Okay.
I'm going to talk about Bott periodicity, quantum symmetries, how they model three minds and 8 states of minds. I'm explaining this and rehearsing this to my friends who you know, John Harland and Thomas Gajdosik in Carlsbad, California, and Vilnius, Lithuania, respectively. I am Andrius Kulikauskas. This is Math for Wisdom. So this is a talk that I'm going to give tomorrow at Vilnius Tech, known in Lithuanian as Vilnius Technologijos, let's see, Vilnius Gediminas Technologijos Universitetas. And this is to the mathematical modeling department, about 20 people. So I have way too many slides, but you're both a bit familiar with this material. I will run through them. It will stop every few slides or so. But I'm starting at the end here. So this is a talk on modeling of the states of a self by way of the three quantum symmetries of a Hamiltonian and Bott periodicity. And I'm trying to say this is the diagram where I want to end up, where I'll talk about the three minds, the conscious, the unconscious, conscious, and consciousness, how they relate to quantum symmetries, how they relate to the two forms of Bott periodicity, real, eightfold real, and twofold complex. So then I define the three minds, saying there's an unconscious mind that knows and a conscious mind that doesn't know but asks, and consciousness which compares them and investigates, and three transformations which ground symmetry. So there's time reversal, which swaps the t with the minus t. There's a mirror symmetry, which swaps the x and the minus x, and there's charge conjugation, which swaps them both, and is the same as swapping matter and antimatter. And so then I'll talk about that. I'll say, look, there's all kinds of, I've collected 350 examples in the history of world culture. So that would include Freud, and that would include Plato, and that would include, all the way back to the Big Bang. And to talk about modeling as a bridge. And so it's a bridge. In my case, it's between wisdom. So I'm going to try to talk the theme of, there's basically three things I'm saying with my talk. What I'm trying to model is this world of wisdom, this world of subjective experience, this world of our inner life, how to talk about that, how to document that, and then how to model that. So that's the first, is that there's this world there I'd like to talk about, and it's related to metaphysics and psychology and culture, but to possibly neurology and evolution. And then the question is about how to model things in general, and then all kinds of mathematics that comes up and it's related. But I'm trying to say, look, I have something to model. I have facts. I'm trying to find mathematics that's relevant, as opposed to the other way around, which would be like numerology, where you find some fascinating mathematical structure and you try to interpret meaning in terms of it. So modeling kind of works both ways. Sometimes you draw more on the math and sometimes you draw more on the facts. But I'm trying to say, in a science, you want to have a really be coming from the facts. And so then I will talk about an example in math. Or first of all, I'll just say mathematically, yeah, this is an example in math, an autoencoder. And so this makes it concrete that this mind that knows could be given by, let's say, 100 billion neurons filtering information. And you can think of it as encoding that information. And you can think of it as compressed into 100,000 concepts, or these could be cortical columns. And the way I think about it is, this is what we don't know. These are like variables or slots or latent, concepts. And so then that can be it could be encoded and it could be decoded. And so in math, we have like an autoencoder, which takes this setup and basically has a algorithm that keeps improving the coding. It could be by trial and error randomly, but it just says, look, this is the input. Let's code it. Let's decode it with an algorithm. And does it match up? So if you have a translation problem, you can maybe do it perfectly, let's say. So the first question is, does it match up perfectly or very well? And then can you get a better algorithm that encodes it into, let's say, a smaller number of concepts, etc. So this is and this can be done. This is an early version of machine learning when we were in grad school at the UCSD. I think this is very much the kind of thing they were doing. Then later on, they made a variational autoencoder, which says that instead of exact translation, you could have a probabilistic relation. So you could try to say, can this probabilistically encode and then decode? And so this won't be a perfect translation, but this would be a very good one possibly, and you can try to keep getting it better. So this is an example of the three minds, and I'm giving an abbreviated version of this for you. But any comments up to here so far? Okay.
So yes, you talked
Yes.
about the three minds, but I don't think you've defined it yet. Have you
Not
actually?
for you so much. I will be defining it back up here.
Okay.
Okay. So I'll have more time for them to.
Okay.
And what I'll do is like I'll stop here and I'll ask them if they understand, and then depending on what they say, I'll go to another example or I'll explain more. So it'll be based on them. I'm not going to be. This is going to be interactive.
All right.
Okay. But now I want to show you this. This is something new, actually, and I think it's very much interesting for me. I've shown you the right-hand side before, and I'll talk about that. But this is the equation on the left-hand side between energy over temperature equals free energy over temperature plus entropy. That's a very, maybe I'll increase it. It's a very simple derivation. You have these two probability distributions, P of x comma y, and you just say, okay, well, this equation just says I can multiply by Q of x over Q of x, right? And I can organize it like this. And then I take the logs, so the product becomes a sum. And I'm writing it upside down like this because I wanted 1 over something, because I know how to interpret that. That's knowledge gained. It's also called surprise, but really I think it's like the knowledge gained. So like if P of x comma y is 1/8, then this will be log of 8, and if it's base 2, that'll be 3. So it's 3 bits are gained by this probability. And so what this says, okay, and then what you do, or what's done in the free energy,
So,
they multiply by
what,
Q of x.
could I ask a question here?
Yeah, go
It's
ahead.
the typical in information theory, typically you do use log base 2. So there's going to be some. I mean, if you want to know the number of bits, you're going to have to multiply by what log base e over log or log base 2 over log base or you're going to have to multiply by a number, right? Or natural log of 2 or something.
By ln, I meant log base 2, but
Oh, I see. Okay.
it's my mistake. Yeah.
Okay. All right.
Okay, that's a good point. Okay. Is that all? So then multiplying by Q of x, Q
That's
of
it.
x, Q of x, and then you sum over x's, and these are the formulas, you see. So it's really saying there's not much to it. I mean, I was surprised. It's just saying it's just a way of reorganizing these and comparing these. So in terms of the three minds now, like if we think about that encoder, what is this possibly saying, you see? So for me, it's talking about you have a probability distribution that could be having a huge amount of information. Like let's say this Y is all kinds of evidence about the world. Let's say it's 100 billion, and you'd like to compress it. So Q of x is going to be, so this is, and the way I think of this gap is, this is the dialogue between unconsciousness and consciousness. So how is that being recoded? How are the answers that we unconsciously get from the unconscious that are enmeshed with the world? How is that possibly recoded or reinvented for the conscious mind? To try to get the same information in the two different forms, given that the conscious mind is pretty much divorced from the unconscious. So, when I see this formula here, I see, first of all, I see that this can be knowledge gained. So these are three types of knowledge gained. and they're with regard to different distributions. But when I see the weighted average over Q of X, I see that as a knowledge lens, okay? That's saying, how are we weighing things? How are we looking at all the different X's, in this different situation? So you're relating knowledge gained with knowledge lens. And so that's like relating the observed and the observer. And in entropy, it's very interesting. They're both the same, but in energy, they're both different. And then in free energy, we have it compared like this. So the interpretation that I give is to say, well, here, well, in entropy, basically, you're using the same distribution for the knowledge lens and for the knowledge gained. And in that sense, there's a kind of equilibrium. Whereas in the case of energy, you're using different distributions between knowledge lens and knowledge gain. So there's like a disequilibrium. The point is that there's different. And what that means, what that suggests, and I think what it means, and I think what makes sense is that if you want to have useful work, you need to be, like if you want this compression to be useful, you need things to be different. If they're the same, the compression is just, especially if it's a one-to-one map is not helpful. It's just pointless. There's no work done. It's useless. So what entropy is, it's kind of like saying, like in this situation where you want to do compression or you have these 2 points of view, you're always going to have this situation where you're looking at what you already, you're looking at yourself, you're looking at looking what's divorced from what you're interested in, actually. And so this is just going to be a useless term. The thing that you're interested is this useful thing that's based on the disequilibrium. And then what this says is that you can break up the two and you can isolate the useful part by saying the knowledge gained will be the useful thing, but with regard to the knowledge lens that you have. So it's a way of separating, this Q of, you introduce this Q of X, but you separate it so that this one will be, this P of X squared will be understood with regard to Q of X, and then this extra term will be on its own. And so that's a way of, I think it's a very meaningful interpretation of energy as useful part and useless part, and why that's natural. Has any comments on this?
That's intriguing. I like it. Yeah.
You like it, right?
Yeah. I think it's interesting. It's an interesting framework.
It's nice, but I don't see what it models.
Well, it's now, first of all, it's just very direct. So that's the first thing. And then it turns out this term has a name in statistics. It's cross entropy. And it's very basic to machine learning because, and then this is very famous. This is the Kullback-Leibler divergence. So this is, they have a metric. It's not a metric because it's not symmetric, but they have a relationship between Q and P. And then when you write it out, it looks like this. And then that's kind of like how well does Q model P, let's say, right? So, but you didn't know what the practical thing of this is? Well, so first of all, this is giving insight in terms of what energy is. Because I think I've spoken and I've looked recently and like people don't know what energy is. If you read Wikipedia article, it's just not defined. It's amazing. So
does it define it?
Well, yeah, this defines it and compares it with entropy. It says,
what is entropy then?
Well, these things are, it's the relationship between a knowledge lens and knowledge gained.
Okay, what is a knowledge lens?
Knowledge lens is how an observer is looking at the world. It's the way that the assumptions that they're presuming, that they're imposing.
In terms of mathematical modeling, it's for me not defined still.
Well, here it's defined as a probability. It's saying like, give me a bunch of states, let's say X. So for example, Y is evidence. X would be the language of this conscious world. So that would be in terms of, typically it's a vocabulary of actions. Like what are the actions you can take? And so even conceptualizing things can be thought of as an action. But this X, so Y is evidence you're getting from your senses. This X here really, I think, should be understood as sensory evidence for an action here. So like if I move my elbow, I can have a sense of where my elbow is located, let's say, right? So that would be what this X actually means. So you have sensory versions of some of these things, and then you have extra things, and then you're compressing this all. So does that make sense what P of X comma Y and Q of X are talking about, or
Not a lot.
not a lot? Well, anyway, so X are your internal vocabulary. Like what are the kinds of things you could be doing? What are the concepts you could have, right? Does that make sense or a little bit, or?
In terms of mathematical modeling, no, it's too abstract and not
Well, X is a set of states. It
okay.
could be 7 states, let's say, right?
Okay.
Could be six sides of a die, I think, right?
Okay, good.
Okay, so you're summing over 6 things.
Mm-hmm.
Now, with each of the sides of the die, you have your own view of how significant that is, or important that is, or common that is, or something like that, relevant that is. So some may be 50%, and some may be 0%, and some may be. So that's this. And then you compare that with knowledge gained. So knowledge gained is surprise, and it looks like this, and it's the number of bits that it would equal, and you weigh them two together.
Mm-hmm.
And the point being that the difference between energy over temperature compared to entropy is that this is a self relation, but this is a relation between different. So it's kind of like the difference between equilibrium and disequilibrium. In order to do work, you have to be comparing two different systems. So like in order to have energy, you have to have the system of the observed and the system of the observer, and they have to be distinct.
Mm-hmm.
And so then it's saying that that's what energy is. But with entropy, it's like what the observer is observing when they're not observing anything else. So it's something, but the idea is that and it's something, but it's not interesting. Another important thing to note up is also the qualitative difference. Q of X can be 0, but P of X comma Y, these things cannot be 0. So that's also giving a clue, like what's the difference between an observer and an observed? An observer can have states that they're observing with 0 probability. But an observed, like in nature, cannot have states with 0 probability. That won't make sense. So that's also helpful to say there's a way to distinguish observer and observer. There's a way to put them together in these 3 different ways. And then you can continue. So like if this is comparing P of X comma Y over Q of X, then you can go here. You can say, well, it can be conditioned on the evidence Y. So we can draw the evidence Y out. We can have X given Y. We can reorganize this. And then you can have, this is called the surprise. And this actually factors out. You could just get rid of the Q here because this does depend on anything. And this would be called this is the divergence. I think the Kullback-Leibler divergence for this particular function, P of X given Y. So anyways, I was just very excited about this. Any more thoughts, John, on this or not? John, are you with us?
Sorry. Yeah, you keep talking about energy, and the way I view thermodynamic systems is it's kind of a game you're playing to extract useful work out of a entropic system.
Mm-hmm.
Thermodynamics is kind of telling you what the limits are in terms of what you can do.
Mm-hmm.
It's not so much talking about nature as talking about the interaction between an agent that wants to game nature in a certain sense. In other words, extract, use the natural processes of nature to sort of to control the world. It's more like a control situation. Yeah, I mean that's kind of I don't know if Thomas agrees with me, but
Yes, I do.
it's more a matter of like you got this entropic system, how do you game it for your advantage? And so maybe in that context, you talk about energy. Really thermodynamics is all about how you can extract energy from a system or maybe other goodies from a system um, that and the limits on what you can do with it,
Well,
or
and so this
how
is,
much
I
you
think
can
this
do
is
that, to what extent you can do that.
this is speaking to it in the sense that it's very clearly defining the difference between the useful work, which is the free energy and the over temperature, and the useless part, which is the entropy.
Yes, that's what that's why I find it interesting. This
And also like it gives different viewpoints on things. So for example, very commonly people say, well, you want to learn as much as possible, right? Like, but when you look at this and think about it, you kind of want to not learn, maybe because um, you want Q of X to be, I mean, you want this entropic term of Q of X to be as little as possible, basically like just be insignificant. So there's a certain sense in which like you don't want to, maybe I'll just give the insight, maybe this is wrong, but you don't want to elaborate Q of X too much or get it too complicated, like over here, let's say, comparing it, because there may be nothing wrong with having surprise, right? Like if you have a bunch of deep principles that you're that are very helpful and knowledgeable, whatever, I don't need to remember all kinds of facts about the world. I can keep it surprising. I'm ready for it because I'm very well organized inside. And so if something unexpected happens, that's not really a problem, because I'm ready for anything in a certain sense. So that's one thing that kind of comes like, how is this Q of X growing or evolving or et cetera, because in the sense that, let's say, what does it mean for entropy to increase, let's say, right? Another thing, in terms of the definition of temperature, I saw a video which I liked, where they basically said that 1 over temperature is much more natural than temperature, because 1 over temperature is change in entropy over change in, let's say, energy, and or especially like, let's say, heat, I guess. But no, I think, but change in energy over, I'm sorry, change in entropy over change in energy. So if you give a system a little bit of energy, how does the entropy change? And I think that, I don't know, I forget how that applies here, but I'll have to think about it. Anyways, this was very exciting for me. And so I'll just rush through the rest of the talk, but I wanted to share that with you. Then I can talk about the Kalman filter. And I wrote the Kalman filter so you have estimates and you have measurements and how do you incorporate them. And I wrote them in this form because I like this because it kind of just makes clear that this combines in the way that the product of a derivative would, right? So that's another example. So these are just some examples to talk about the 3 minds. This is the 3 minds in terms of action perception loop, and that the consciousness can be a break for that. And then you can look at that. It can look as a 2 cycle, which is relevant for the unconscious, or a 4 cycle, which is relevant for the conscious. So these are just things to talk about. And so that's the introduction to the 3 minds. And then I say, okay, what I want to do now is to talk about these 8 divisions of everything, like states of minds. And I'm going to relate them to 8 collections of, or combinations of quantum symmetries, and these 8 symmetric spaces, which are basically, these are versions of Bott periodicity. And these are well, this is where the Hamiltonians will come from. So then I give a talk about the divisions of everything that you know about, the 2-sum, 3-sum, 4-sum, 5-sum, 6-sum, 7-sum, the null sum and the 1-sum, and then how they all fit together. And then I go to Bott periodicity and I explain that, okay, this is the original form of it in algebraic topology, this sequence Z2, Z2, 0, Z, 0, 0, 0, Z, let's say for the orthogonal. And then I'll say, okay, well, let's look at example of Z2, 0, and Z. So 0 would be like if a loop on a sphere shrinks, that's all it can do. So that has fundamental group 0. And in a circle, you can wind it forward as many times as you like, and you can wind it backwards as many times as you like. So that would be Z. And then RP2 is like, it's the projective sphere. And I thought about this, so this is Z2 is the fundamental group. And so what it is, you know, but I'll say, is you have a point on the sphere and you identify it with its antipode. So it's basically like half of a sphere in a certain sense. And then it's almost like, you can move on one side and you can move on the other side, but they're basically one. So the question is, well, why is this Z2? And the reason is that if you pick a point, you can make a path to the same point on the other side, and that'll be that'll be a loop because you've gotten back to where you started. And then the point is, well, if you have two loops, why are you able to shrink that? And this kind of bothered me. I didn't know. But then I understood, oh, the reason is this. When you have two loops, you see, you don't have that obligation anymore that they have to be 180 degrees apart. You see, in the first case, like if you have a point to its antipode, you're saying, okay, we're going to go to the other side and it's going to be the same point. And you had that obligation. But when you connect another path, it's only the first and last point that have to match up. So whatever obligation you had here in the middle, that goes away. And so then once that goes away, you can just take this, you can shrink it down to that point. So that's C2. Any comments on this or?
Yeah, that's a nice, I think it's a nice explanation. I like that.
Yeah, I was. And so then this relates to the homotopies of spheres. And so I couldn't even explain this, but the point is that you get Bott periodicity, something related to Bott periodicity, when one of the spheres gets much larger than the other in terms of dimensions. Then in terms of, I define, okay, well, what is the orthogonal and the unitary and symplectic? I need to define them. And so I just say, well, look, for geometry, you need an inner product. So here's an inner product. And then you have, like, let's say you have orthonormal, like would be an independent. Let's say you have an orthonormal set of vectors, so they're all independent. So if you take those rows and you multiply them, well, so if you take these rows, if you take one vector and you multiply with the other vector, you should get 0 or 1, depending on what it is. So if I write them this way and line them up, and then maybe take the conjugates as needed, then I'll get this relationship. So that's Q times transpose with a plotable star.
But if you go to I mean, I don't know if you need for geometry a scalar product.
Well, I think depends on how you talk about geometry, and I think there's different layers of it, but at a certain point you want to have a notion of length. So
if you have a notion of length, you have a scalar product, but you can do geometry without having a notion of length.
What kind of geometry do you think about?
Euclidean. You just ask what is parallel.
Oh. For example, yeah, there's all these constructions you could do without a notion of length. That's true.
And
okay, so
if you use that you want to have a scalar product, yes, you can talk about it, and then you have this distinction. But
yeah, that's a good. Okay, so that's a good thing. Maybe I need to fix this, or I mean, would you have comments on that, John?
So I'm sorry, I didn't quite hear what so you can do geometry.
Well, Thomas is just pointing out that like I made this claim that, oh, well, for geometry you want an inner product, you need an inner product, but John, I mean, most of the traditional Euclidean geometry, you don't have any notion of length. It's not really relevant. So why would you need an inner product, right? Like so.
I mean, if you write you want an inner product, then it's fine. But if it's necessary, then mathematicians might object.
Right. I think that's a good point. I think it could maybe fix that.
Although it is a typical, refrain in mathematics that, this is how you connect algebra and geometry through an inner product.
Yes, if you want to have it, if you want to algebraize it or so, then yes, you want it, but...
Okay, so that'd be for algebraic geometry, do you think?
Yes.
Is that...
I think so. For that, you have to some extent talk about it, define it, do something, but I'm not as...
Okay, that's a good comment.
Serious in it.
Yeah,
that's why I'm talking to the experts. So yeah, John.
Well, yeah. I mean, I don't know. I'm not an expert in geometry, the different kinds of geometries that exist, but certainly, if you want to do differential geometry, you're going to have a,
yes.
if you talk about manifolds, you're going to have at least some kind of, yeah.
Okay, and the point is that there's not that many inner products, I guess, or that's what this is saying. And so then you have these symmetric spaces, and then they're all embedding. You have these embeddings, you have these linear complex structures. I'm saying that they're mapping perspectives. And so then there's this commutativity, anti-commutativity.
Yeah.
And then I give the example of, let's say, U and O of 2K and U of K and how it splits up. using the J1. And this is rotations, and this is rotations times a reflection. And then that's, I think of the reflection as indicating consciousness as opposed to unconsciousness. So at least it's helping to model that. Now here's the Harland construction based on the two Morse sequence. And it's just very elegant. So once you have the two Morse sequence, you just write it like that. And this is the unreduced representation. Is that correct, or does that
I think
say?
that's right. Yeah.
Yeah. And so this is really profound. And the two Morse is something to look at because this comes in later. And it keeps flipping things around backwards and forwards. And so this tells you how these things are growing by 2 dimensions. You're doubling each time. And so then you can compare that. Well, this is an example of the reduced, irreducible. So these are not growing like that that they're changed. Like here, it's 2 times, these are blocks, 2 by 2 blocks, 4 by 4 blocks, but then it's 2 4 by 4 blocks, and then that's an 8 block, and 8 by 8, 8 by 8.
Oh, but those are reducible. Aren't those
These are
reducible?
irreducible.
Oh, okay.
Well, these are because these are.
I mean, but the, the 16 by 16 Lie group matrices of Lie groups of matrices have reductions, right? I mean, when you get up to
Well,
like,
this would be M16. These are for Clifford algebras, right? So these are for.
okay,
This is for generating Clifford algebras.
okay, but the corresponding Lie groups that come out of these are reducible, right? Um, at least the one, you demand that they commute with J2, J1, J2, J3, you get reducibility, right? I mean, that's when things start collapsing. That's how so I'm not quite, what is
Not
reducible?
quite sure what you. I'm not sure. Like, I guess what I'm trying to say, I may have to be very careful. If you look at Clifford algebra representations, um, I think these are irreducible representations. Now, of course, I've multiplied them here. Like, so I would look at the 2 by 2 here, right? The 4 by 4 here. This is 8 by 8.
So maybe yeah, I mean, something's reducible and
8
something
by 8.
maybe isn't, but the Lie groups that result from demanding that you have commutativity with these, um, like the Lie groups that are subgroups of O16, those reduce, right? I mean, that's part of the shtick.
Yeah, but these aren't that. No, these are the J's. This
Yes,
is what
okay,
the J's are generating. The J's aren't the J's are different from the Lie groups,
okay, okay. So you're
right?
talking
Because
just
the
the
J's,
Clifford algebra.
yeah, this is the Clifford algebra. These are the J's. Okay, so that's an important point to make. But this is
Okay,
looking from the J point of view, right?
okay,
As opposed to what's anti-commuting with them or what's commuting with them, right? And so then this is where I introduce Clifford algebra generators, and that they're choices. Let's say they're perspectives. They're also choices because of and then that this is how it goes with Bott periodicity. And then this is the classification of superdivision algebras. And so this is again an example of the 3 minds where you have like the bosonic first mind, you have this marker and this like reflected fermionic second mind, and then you have the automorphism that links them. And then I said, okay, now you can look at these topologically, and then you can think of these as perspectives. So if you look at the off-diagonal block, sometimes it grows and sometimes it doesn't. So if you start with the with the identity, you get a 2 by 2 block that's growing, and there's an off-diagonal component, and so that grows. And then when you go to 4 by 4, it grows again. But here, this upper part is just the product of I and j. That's k. Then you add a negative k on the bottom, so that would be algebraically independent. But then you don't have off diagonal, so it's not growing here. But it's growing here. And this will be an isometry. It's not growing here, it's not growing here, it's here, it's the same as like with k, like you have 2 copies of it, but it doesn't have, and then it grows again. So the Z2, Z2, 0, Z, 0, 0, 0, Z is related to that, or it's expressing that. Any thoughts on this part?
Hmm.
And I'm trying to say that, well, this is really like this shift from here to from the 0 to the 1 sum, say, or in the 2 sum, the shift from, let's say, free will to fate, that's happening because of this. And what this is doing, this off-diagonal thing, the off-diagonal is when you look at those superdivision algebras, you have the latest choice. You're saying basically you have an information. If you add a new generator, you're basically getting another copy of what you had before times that generator. So now you have these two copies. And so those even and odd will be related by these off-diagonal components. So if they have a non-trivial relationship, then that's when you would get a non-trivial topology, I guess. That's maybe what's up. Does that kind of make sense? Or is it, I don't know if that's.
I mean, I haven't seen this before. And it's a bit beyond me.
Yeah, it's a bit beyond me too.
I kind of see where you're going with it. I mean, I see the pattern, but I don't really see the connections with other stuff that you're speaking of.
And this is coming. I think the reason I've noticed this pattern or whatever, because it's coming from this whole Z2 graded thing, like where you have a Clifford algebra and you say what are the even and the odd things, and in the representation I was going even odd. And basically, if you go back here to the superdivision part, if I had that, yeah, you see, it's based on choosing the last. It's whatever is the last thing. That's the last generator that you've chosen. And if you look at these are like choices made, in the probability point of view or the binomial theorem point of view, right? Like you added the third choice here. And how is the third choice combining with everything before that, let's say, right? Or whatever. I think that's the deal. Anyways, so then I talk about how the vector space splits if you have a triple product like this, that normally it squares to -1, or it squares, this squares to -1, but this squares to +1, J1, J2, J3. And so that means that you're going to get two vectors spaces, V with eigenvalue +1 and V with eigenvalue -1. And then you have an isometry based on that. So it's taking V +1 and mapping it to V -1, vice versa. So I'm saying that relates, that's like this L, that because it's, that relates this with that. I think it's that isometry. And then we see that L, something like that L, we see it in the Octonions, because the Octonions have the IJK for the quaternions, and then they have this mirror L, or like looking glass it's called sometimes, and they go Li, Lj, Lk. And what it does, it says like, because it's non-associative, it says if you have La in parentheses times B, then you'll reverse the order of the A and the B. You'll go L, and in this other world, it becomes a BA as opposed to AB. And then just noting that the projective line for Octonions generates Bott periodicity. And that if you go through, you can write these out, these J1s through, with the L that I had over there, you can write it that you have J1, J2, you have the product, then you have them all, and then you subtract the J1, you remove the J1, you remove the J2, you remove them both, and you get this. So that's a way of kind of saying there's some kind of possible connection there with the Octonions. And this is a little bit memorable with the, I don't know, I guess not, the 2 sequence. There could be a connection here with that, with the 2 more sequence here. I don't know. And then J9, explaining that J9 forces you to redo all these, because if you assume that all these had like an infinite diagonal, component, just going, just repeating down the diagonal. The problem is that J9 needs to be a 32 by 32 matrix. It would consist of 4 16 by 16 blocks. Any of one of these would be a repeated block on the diagonal. This would need to anti-commute, but then you'd get equations looking like this. that means that any one of these matrices would anti-commute with all of these. But these don't anti-commute with all of them because they don't anti-commute with themselves. There is no, this is a full set. So it's not possible to have another one that would anti-commute with them all. It'd have to be 0. So that means that this is not going to work. So then a solution is to rewrite all of the matrices so that they look like this on the infinite diagonal. And then you can have J9 contain this.
So that's the price you pay for irreducibility, I guess. For
Yeah,
reducibility,
because you didn't have to do that,
I didn't have
right?
to do that, but the thing is, I had to grow. My construction had to grow, whereas yours doesn't. But then you get hamstringed by you just don't have enough dimensions to be able to.
Right. And so that's something we can, I can chase down, or we can do that together. But like, that's
Yeah,
very interesting. Like, how does that change, right? So,
yeah,
and that you solve it once, you're going to have to run into the same problem again, because what's happening is like, okay, the J9 is like this. You can see how they're going to grow from now. They're all going to be like these huge 16 by 16 matrices, right?
Hmm.
And then you're going to have to go bigger again. So I think that's happening here. So then I say, okay, well, that was Lie groups, but now we're going to talk about the Lie algebras. And so then I just explain like that instead of, well, you're going to have, e to the whatever, and t is like time, basically, but e to the gt as opposed to g. So this will be orthogonal here will mean like anti-symmetric or anti-Hermitian or quaternionic anti-Hermitian. And so that's here. And then the Hamiltonian gets introduced, and the Hamiltonian's coming in as this, I times the Hamiltonian is this component that is will be the anti-symmetric part when you go from the JK to the HK to the subalgebra. And then e to the IHT would be in the symmetric space. So for every Hamiltonian, I guess you have a point in the symmetric space. That's how it works, or vice versa. And then this suggests the divisions of everything, which I'm interested in. So you have the embedding of the Lie groups, and so Lie algebras, and then, okay, O16R, I'm saying that's everything. And then you have a Lie algebra and then a subalgebra, and you have this part. And JK anti-commutes with this part, and it commutes with that part. And so then you can extend it and basically divide, you can think of this as everything, and you can divide it into however many perspectives that would be. But what this means is that you have a different Hamiltonian at each point that you're picking up, and you're summing these Hamiltonians, right? So what happens if you're summing Hamiltonians like that?
It sounds like perturbation theory to me. Like
Uh-huh.
I don't know, Thomas. I mean,
I
like
mean, can you sum Hamiltonians and get a new Hamiltonian? You should be able to, right? Or,
I mean, the Hamiltonian is usually of a system, and then you have one. So you need another consideration, another viewpoint, another part with which you add, and then you add something. Then it can be like perturbation theory, but it can be also you add a new interaction, you add a Hamiltonian for it, and I mean, you extend your description of the system by it.
so just for my baby mind. So Hamiltonian's additive in the way that energy is additive. It's just that normally you wouldn't add it because you're only working with one system. You have a system, and then there's nothing to add, right? Like it's just a given. Right?
And to some extent, if you try to look more and more accurately, the energy that you add will be very tiny then, and then you look at how energy is split with the new effect that you add, the new piece for the Hamiltonian that you add.
And so this brought to mind John's agency hierarchy, you see, which could be like a perturbation hierarchy or something like that. So that was I don't know if that makes sense.
Yeah, but I mean, perturbation theory for me is something that is not finite, but you write it out as a finite series. And a finite series that actually has to terminate because after 8 pieces, you are back at the origin. So there's nothing more. So it's...
Well, yeah, I guess.
So in perturbation theory, you can go to any order that you want. And basically,
Well, this is like this looks to me like orders of scale, like orders of magnitude,
yes,
right? Like that there's and that there's different things going on in different
be,
orders
yes.
of magnitude. And so each of these is contributing a perspective. Any thoughts on this, John, or?
Can make sense for me at least, yes.
Yeah, I'm sort of lost in the weeds there. You're saying it adds a perspective, so in a sense, you're expanding the system. Is that
Well, this is a division of everything into perspectives. And so the question is, that's the whole point. Like, so
I
this
mean,
is, 5 perspectives, let's say, this would be G naught
example
minus.
could be, I mean, I think John knows it definitely. If you look at the Schrödinger equation for the hydrogen atom and you add corrections and corrections that make it more explicit what the energy level of a certain state is, means you split fine splitting, hyperfine splitting. So it's each adding a term to the Hamiltonian that adds a new interaction that you think is much smaller than the one before. So in that sense, it's perturbation theory, but organized. And you do it just with all the corrections that you can think of.
It's like levels of sophistication.
Yes.
And this is a way
I
of
think it makes sense
metaphysical.
like that.
Okay. And so then I start showing like the calculation if you continue and, so let's go through this through far, and then I go them all together. And then I explain that the Hamiltonian, and so basically this is coming from 2 different papers. One is the Stone-Chu-Roy recipe for Bott periodicity, calculating this J1, J2, J3, and so on. The other one is for calculating the quantum symmetries and the Hamiltonians that are constrained by them or, reflect the particular symmetries. And so then trying to match them up. And so that's basically, and I need to go back to that and try to get better understand how the 2 accounts link up. But anyways, and so then just some comments about the Hamiltonian, how it can express identity or a self in the sense that it's coherent and it evolves in time and it aggregates all of the the dynamics modes, that it can go through. And it's self-adjoint and it's an Hermitian matrix. And it affects its context and is affected by its context, which is the way I read this self-adjointness or this, I think this part. So it has those 2. And so then I give, in the many-body system, the way the Hamiltonian would look when this is called, I guess, the second quantization, whatever. Typically, you would have an infinite many of terms, like so, because you could have 2 this is like 0 interactions, 1 interaction, but it could be 2 or 3 or 4 or as many as you want. But this is like a single thing with itself, basically. And so then you have and I write the dagger as star T just to kind of be more, maybe for my own sake, just to kind of keep from having all kinds of different notations around. And then this would be creation and then annihilation. This is a row vector. And then let's say if it's diagonalized, it would look like this. And then this would be annihilation. Does this look plausible or?
Annihilation, I don't know, but I mean.
Those creation operators and annihilation operators. But does this Hamiltonian look plausible or?
Yes, but I wouldn't write them as creation and annihilation operators. I mean, they're just the operators that you connect with the Hamiltonian. The states, depends if you want to write them as creation and annihilation operators. It's
okay. Or well, anyway, this is kind of lifted from that one paper. And so the points are that in the situations that we're looking at, you have particles versus wholes. Particles have positive energy. 0 energy is forbidden. Oh, it says here, I should write E does not equal 0 anyways, but well, equal 0 is forbidden. That's what it says here. And then you can have negative energy, which be a whole. You can have, and so basically, you can have a symmetry where, and this would be more clear, like if you had n particles. So let's say you have one particle among n, where like 1 is defined, or let's say 1 is created, is the same thing, can be mapped to n particles all being filled and then having one whole. So you can kind of map that to that. So this is probably like not the best picture for that, but that's where you get these extra symmetries. They're called transpositional symmetries, transposing symmetries. If you swap H to minus H, that's just renaming the particles and the holes. But if you swap H to H transpose, which is like H star, that's like inverting the direction of causality. So like what was creating becomes and annihilating gets swapped. Okay. And I'm saying that's like stepping in and stepping out in terms of perspective. So this is that's how I interpret it. And then with the symmetries, they can be linear or antilinear. They can be ordinary, or like I was saying, transposing. We don't allow for the ordinary linear ones, and then that partly because that forces us to have at most one of each of these. And then you can have time reversal, charge conjugation, and then mirror symmetry. If I just threw in Wigner's theorem, just if someone asks, I can just point it. This is Wigner's theorem being important because that's saying that these quantum symmetries have to be either linear or antilinear. And then that's I'm not even going to talk about this, but that's what it goes. And then saying, okay, then you get these natural bases, which depends on the symmetries you choose. So if you write 1 over p comma q as a bunch of ones on the diagonal, followed by a bunch of negative ones. If you write jm as 1, negative 1, like that, bunch of ones on that block and a bunch of negative ones on that block. Well, when you have a single symmetry, either you have one symmetry, if you have two, you also have the third. So, but if you have one symmetry, let's say a time reversal, then you would like to write it in this form because that would be the most natural. So if you have C, if it squares to 1, if it squares to minus 1, you'd like to write it something like that. It would be most natural. But when you have 3, then it turns out the natural thing to do is to use the US as the natural basis, and then you have to write these accordingly. I didn't finish this, I'll have to write this in. And so that's an interesting thing that kind of, in terms of calculating the Hamiltonians in a nice way, you end up having to switch what is the natural basis as you go back and forth. Here's just a picture of the board I was working on. Here's just going back to the calculations to sum up, and then this is the final picture saying how it all comes together. That when you combine those two, you get this picture going around. And one of the nice ways to think about this really is just a 4 cycle, in a sense. And it's about transcending, let's say like you start off, let's say with, well, it turns out that the C stands for what's inaccessible, which is related to the conscious. And the T stands for what is accessible. And this comes from lining it up with the divisions of everything, lining it up with J1 through J2, lining it up with all this. Then you start to get a picture. And so lining up with this metaphysical intuition you get from the quantum symmetries. But when you all line it up, then this is the reading that I get. But that the C has to do with the T has to do with what's accessible, the C with what's inaccessible. The squaring to +1 is the unconscious. Squaring to -1 is modeling the conscious. When you put it all together, it's basically saying like the unconscious, let's say, knows something. That would be right here. To transcend that, it goes beyond what it knows to what it doesn't know. Okay, so now you have a zone where the unconscious doesn't know something. To transcend that, somebody else has to know something within that because the unconscious doesn't know. So that's how you get the conscious. The conscious knows something. And then the conscious transcends that, its knowledge, by going on to what it doesn't know. And then the conscious doesn't know, so then the unconscious creeps in to say, oh, okay, I can know that. So there's this like a trigonometric 4 cycle. The point being that when you hand over from one to the other, you can have both at the same time with the third. And so then you have this 8 cycle, but you also can think of it as a 4 cycle. So that's and then so you can add +1 as we did with the J1, J2, J3, but you can also be adding +2 at a time. That relates to an adjunction, loop space adjunction that I have to study. And it should be possible, according to my wondrous wisdom, to be able to add +3, which would somehow be maybe +4 - 1, I don't know. Make sense of that. And then finally, just to conclude, like the S can stand on its own. And so it, this is another form of the three minds that I think is very interesting. It's like in quantum foundations, you have states, you have observables, you have measurements. So the states are the answers. Observables, I think, are like variables, are like questions that get answered. And then the measurements are putting them together. And so if you think of that, so the time reversal is, I mean, or let's see, I think time reversal, like it has to do with the answers, the states, and then charge conjugation is, according to this, would be related to the observables or the questions, and the measurement combines them both. So what it basically says is that if you combine these here, then you can go over here, have the measurement, you can let go of those two. You don't need to worry about them. It can stand on its own. So for me, that's like the collapse of the wave function, saying that once you have a measurement, the measurement doesn't have to have the other two with it, and it can stand on its own. This would be like the classical world, speed quantum world. In terms of metaphysics, this is a world where you have that, like I was saying here, these symmetries, I've written them all in terms of unitary matrices, but then you have to go between H and H star. If you wanted to go between H and H, you'd have to have anti-unitary matrices, like UCK, K being the reflection. So if you go between H and H star for time reversal or charge conjugation, then that's the 8th cycle, which they build up right here. And then that's like me as a person, an individual. And when you have a personality individual, you can step in to your context or you can step out. But when you're living as a person in general, just like any person, then that doesn't make sense. That doesn't apply. So that's the metaphysical. And then finally, just to say, like, these types of shapes appear, like, sulfur naturally appears as an octo form. It has Z equals 16, which is kind of curious. The Krebs cycle is an 8th cycle based on enzymes. And so it's possible that this template is at, in work on level. But regardless, I think that my think is that these three minds in the example I show, they predate biology, they predate chemistry, and they predate natural selection. Like there's something, I think, metaphysically deeper here. Or at least it's in the mind, but if the mind is telling us anything useful about the world, it does predate those things. That's my talk.
Yes, a comment about the last slide. It puts you again into numerology. What is the connection of S8 to your state? Which of the atom describes what? Can you?
I don't know. No, this is something to look at. This is something to try to understand.
I don't think so. I mean, this is a sign for numerology for me. Because it's a cycle of 8 things, it should be.
No, it's not. Well, it's not any cycle of 8 things. It's saying that if you look, I mean, it's saying, look, sulfur is implicated in the origin of life. Like, so for example, sulfur comes in right here.
And?
Well, and
but
so
it doesn't come in like S8. It comes like one atom in your
that's true.
Molecule.
Sure, but this is the natural form, and then this is the.
This is the natural.
This is a ubiquitous. I'm just saying, that's something that I notice, and I think of. I mean, I just keep it in my mind. I think that's. I don't know what you think, John, but I know that.
Yeah, I mean, I think it does smack of numerology, but it's on the other hand, you're trying to convey something, maybe something a little bit vaguer that may be lost on the audience. You're saying that fact that this, which the Krebs cycle, which it's part of metabolism, right? That's how energy is.
Well, it's ubiquitous, right? Like every single cell in the universe, I mean, on the planet, let's say, has the Krebs cycle.
So.
Right. So
how does it relate to your modeling? Well, this is what is missing, and this is why it really smells of numerology.
I think numerology is the opposite. I think numerology would be to say, no, I think numerology is the opposite. Numerology is if you start with something like E8 or, and like this is typical numerology, like, you take E8 and you say, I think this, I think I can do the standard model in E8. Okay, well, go ahead. But like, why? Do you see, like, that's numerology. You're starting with
No.
math. Pardon?
I wouldn't say it's just trying to find a representation. Maybe it's more convenient to write it down like that.
Well, anyways,
don't
but
tell anything more.
well, to start with the Octonians or something like that. But physicists, there are physicists who do this. You know, they pick something that they think is mathematically fascinating, and then they try to say, well, where does it come up in physics? I'm doing the opposite. I said, look, I have this metaphysical data that I have.
Yes.
I found
That's
a place
fine.
to do it mathematically.
Yes.
Now I'm saying, look, here's another thing to look at. Now, the S8 maybe not, but like here's this Krebs cycle, right? That has a similar type of flavor.
No, it does not.
For you.
Yes, for me. I would say for any other experimentally driven person, it says the same. You connect philosophy to now something that doesn't have philosophy as a content.
Well, look, I started with philosophy and I ended up with the tenfold way in physics.
Yes, but then you have to show what is the modeling that you do with your Krebs cycle. How does your Krebs cycle map to your mathematics?
Well, that's the first step in an investigatory project, to say, look, this is something to no.
So you show now something that you will like to work on.
That's what I'm saying, sure. That's what I'm saying. All I'm saying is that, it's very interesting.
The project will be working on the Krebs cycle.
Well, it's a future project, sure. If I
And
can.
the next is finding out how S8 is connected.
Well, let me put it this way. If I can show that the Krebs cycle is Bott periodicity, right? Like that is very interesting.
Good.
Then it becomes like, well, okay, where did that come from? How did that evolve? The fact that S8 is implicated in the origin of life, like why,
I don't
how?
think that S8 is implicated.
Well, not S8, sulfur is implicated. Sulfur.
Okay.
But S8 is the natural form of sulfur.
S8 is the natural form of sulfur in certain conditions.
Planet Earth. Yeah.
On planet Earth at low temperature, definitely not in the center, definitely not in connection when it's bound in materials, which most of it is done, only if it is first basically put into gas form and then condenses, and then it forms this S8. But it's not, it's the natural pure form, maybe, but it's not most of the natural form of sulfur appearing in our planet.
It doesn't have to be, this is just how my mind works. I'm just saying, like, I collect things, I put them in little boxes and I keep them away, and then I...
Yes, but I strongly suggest not to show the last slide.
Okay.
They might jump on it and say, now, okay, what?
Yeah.
What put you into the box of numerology? It's not that you are doing numerology. Okay. It looks like, it smells like.
Okay. Okay, so then I think I'll take that out. Yeah. So I'm going to put in the last slide. The last slide will be here. This one.
From the point of view of
music, I have to make this like warm thanks to John Harland and Thomas Gajdosik for telling me not to put in this slide.
Fine. Yes, I can live with that.
Okay.
All right. And I think even a more intriguing example from my point of view is the diatonic scale in music. You have 7 scale gradations, and then when you get to the 8th, you're back to the beginning, right?
Yeah,
it's related. And
it's actually another structure, but yeah, there's another structure.
And the thing about it is that each of those tone gradations has its own character.
Well, there's a structure where like 2 and 5, 3 and 6, 4 and 7 are, have a relation.
Yes.
And there's a structure. So that's a different structure. That's not this structure. See, I'm just telling
you. Yeah. I mean, you might connect it even to ancient Greek philosophy and say, oh, I have it too. I mean, I can explain.
Plato will explain. So any closing comments? I really appreciate your...
Well, there's a lot. There's a lot. I mean, Thomas and I have seen, bits and pieces of this over the years, and it's still, there are parts that are, like when you go to that final slide and you go from, symmetric space and Hamiltonians to the final metaphysical connection, it's still... and you talk about accessibility and inaccessibility and so forth.
And they combine for definability, right? To be definable, you have to be from accessible and inaccessible. You have to be able to go both. That
Yeah,
makes it
so I mean that really begs elaboration there because
yeah. True. That's fair.
it's really there's a lot of ideas and so
Well, what's the strong parts, let's say, of the talk? What did you think are the parts that fascinate
well, I mean, it's strong. I mean, you do a good job with all the connections with Bott periodicity for sure. I mean, these are, you kind of synthesized a lot of connections there, and I think
Mhm.
so they might appreciate that, and also the connection with neural modeling and free energy. I think that might ring a few bells there. That's the connection with metaphysics is again your own language, and it's very hard to grasp. It is. I mean, if you don't have time to unpack it, and that's the problem, is that it seems like a big jump. Like
Mhm.
the individual mathematical components are kind of nice, for people to see that you know, there might be some interest there, but in terms of the relationship to metaphysics, it's it's hard to jump on that train without having more background. And even with more background, it's difficult. It's difficult to follow.
I mean, this was helpful for me to see that it could be done in an hour, but for people who already know most of it. But to say, yeah, so this will be like, several talks. I think my emphasis tomorrow is to try to get across the three minds. First of all, to say, like, does that make sense? Can they understand that there's no three minds? And then maybe if there's time to kind of say, well, there's this thing about periodicity, like that would be interesting I could give more talks about, like to kind of give a preview of what I would talk
Mhm.
about if I had more.
Yeah.
I think that's to give a talk and a half. I think that's the way. Any other comments about the talk? Oh, and also I'll make it interactive. Like I want to know that they understand. So I think just focusing on the three minds and having a discussion about that, and things like the Kalman filter or the free energy or the encoder.
I think what might help them is if you give a more concrete way how you model. So
Hmm.
giving a concrete example, and there probably the best is really this machine learning or some
Hmm.
sort of language, how to say this is what I could model and I want to do it general,
Hmm.
so that they have something to some extent play with the imagination at least.
Right.
Yeah.
And I think that was nearly coming over.
Hmm.
I think also with this autoencoder picture, what you want to do and where you then explain thermodynamics. But coming there with thermodynamics immediately is, I think, too fast for understanding what you actually want to
Right.
model. That you don't, I mean, you overload the person.
Yes,
Yeah,
exactly.
it is. Yeah, it is an exercise in overload, this talk. I mean, I think you maybe you could frame it. I know you're going to give this talk, but maybe you could frame it like this is sort of a tourist view
Yeah.
of this circle of ideas that I've been working with,
Yeah.
um, and it's got connections with machine learning, evolution, physics,
Hmm.
but the grand picture is a this metaphysical context that you've been working on basically your entire life. And
Right.
so it's just sort of like I mean, if you just present it like here's some of the ingredients um, and with the idea that it's it's a view from 10,000 feet.
Right.
Here that and if this rings a bell or this intrigues anybody, we can have further conversations. We can break this down
Mhm.
into further talks. But you know, it's a circle of ideas that seems to subsume much of physics, much of mathematics,
Mhm.
uh, and and possibly, a complete metaphysical theory, that if it's built completely out. So it's a big project, I mean, it's much more than most people or even communities of people take on, So I mean, that's the thing is you have to maybe just tell them it's very large scale, and these are the ingredients that, and it's kind of a tourist guide, it's kind of a tourist walkthrough, a quick tourist walk through this this uh, this conceptual space that you're working in, and so I mean, in the end, the impression is there's these ingredients, these ingredients, these ingredients, these ingredients, it goes on, and in the end, you're pulling it together in this kind of metaphysical cycle. In the end, this divisions of everything, um, and so since it's so large scale, it is a challenge. Like, how do you give people a taste of this without just making it look like a bunch of disparate ingredients? And I think that maybe some framing, if you think about how to frame it so that people you're going to tell them that this is the way the talk is going to go. It's not going to be
Right. I think
yeah,
that's why. And I started with the end, like to say this is where I
yeah,
want to go,
yeah.
but this is a long way to.
And then, hopefully it stimulates more discussions, more interest, and you can always break it, you could do to break down everything here is a big project.
I'm glad I did basically complete all these slides because it is possible to run through and see, to the end. Like you can climb the mountain, or you can scatter up the mountain, but that the focus is on the beginning. Like, can they understand anything? Can they understand, like, any of those beginning examples with the three minds to say, okay, here's, these three minds. What am I talking about? How can they be expressed mathematically, one way or another way or a third way? I think that's, and then would you like to have more talks about this? But this
Yeah,
is,
it
thank
could
you
be.
very
And
much.
there could be people there that know quite a bit about each,
Yeah, and that they could tap into some of their subjects.
and
That would
say,
work.
yeah, that's related to some work they're doing, and maybe have additional conversations. I think that's kind of the point of this is to show people where you're at and maybe continue,
Mhm. Very good.
continue future conversations, investigations, whatever. It's not to
So
the full
we
expert.
had a full hour. Just maybe to conclude, like any concluding thoughts, Thomas, or a prayer for us for tomorrow.
That it goes well tomorrow and
Yes.
that the audience is open to new ideas, because otherwise, if they just want to see, can I supply my modeling skills and take over the project, then it will not work.
Mhm.
So
Yeah.
that's open minds and
Let,
willingness
let us know
to.
how it goes.
Yeah, I will. Thank you for watching this video. Please go to mathforwisdom.com or simply read the description to this video to learn how you can join our Math for Wisdom discussion group and our study groups. Thank you for liking this video, for subscribing to this YouTube channel, and for supporting Math for Wisdom through Patreon.
I became a Math for Wisdom Patreon supporter. I went to the webpage, patreon.com, found Math for Wisdom, and after just a few minutes of filling a few things out, boom, I was a Math for Wisdom Patreon supporter. You can do it too.